Hello everyone, we have discussed about refraction in the last class, so let's continue from the concept of dispersion. If you have seen a white light passing through a prism, you'll find that a rainbow color comes out, right? Basically, VIBGYOR, they comes out as separate light. Now, a phenomena by which a white light or any two or more wavelengths, they get separated, that phenomena is what we call as dispersion of light. You find the same phenomena happens when the rain stops, the sunlight passes through rain droplets and forms a rainbow, right? So before we understand why a rainbow forms, let's understand the concept of dispersion. So say this is a prism and I'm shining a red light through it first, okay? So that's a normal here. Normal is nothing but an imaginary line that is drawn perpendicular to the surface, and since the ray is traveling, this ray is traveling from air into glass. Since glass prism is made up of glass, it bends towards the normal. That's how it bends, right? Now this ray is going to emerge out of the glass, that is going to travel from glass back into air. So let me draw a normal back here again. A normal is a line that is perpendicular to the surface, and this ray is now going to bend away from the normal since it is traveling from denser medium to rarer medium, right? Simple. We have already learned about refraction, and this is the concept of refraction. Refraction is nothing but a phenomena by which a ray bends either towards the normal or away from the normal when it travels from one medium to another medium. Now, I'm going to shine blue light parallel to my red light, but blue light is not going to bend as much as red. It is going to bend even higher than red. For example, if red was bending 30 degrees, blue will bend 10 degrees. That means it is bending more towards the normal. Clear? Let us understand why. Why does blue bends more than red? Okay, so if this is the wavelength of a red, that's the wavelength of blue. So in a given same area or in a given same length, red has only one wave, whereas a blue has 1, 2, 3, 4 and 5. So it has about 5 waves. So if I'm talking about a given area, which of the color has more wave interaction? It's the blue one, right? Because in the case of a red, we have only one wave interacting with the space, whereas in case of blue, in the same given space, the blue has about 5 waves interacting. So more the interaction with the medium, it loses more energy to the medium, and therefore it slows down further. And we have learned in the last class under refraction that more a wave bends, it's due to more it slows down, right? I gave you an analogy of a car. Like if half portion of the car slows down, that means let's say the left portion of the car slows down, it's just going to stay in behind, and the right portion of the car is moving forward, right? You can see that gap is moving forward, due to which the entire car will move like this. It was always move towards the slow moving portion. Why? Because the slow moving portion will not let the car to go forward, and it was always try to pull it towards its end, and therefore the car will bend towards the slow moving region, right? Now more slower the car is, more it will bend towards the slow moving portion. Similarly, blue slows down further compared to red because blue interacts the most. In I'm talking about blue interacts more than red, therefore it loses more energy to the surrounding and it slows down further, due to which it bends more than red. That's what I'm showing here in the diagram, that the blue bends more than red. And similarly, when blue emerges out in air, it bends further away from the normal more than red. Same reason, because blue was very slow compared to red in glass, and as soon as it enters into air, there is a drastic change in speed compared to red, and due to that huge amount of change in speed, it bends further away from the normal, right? So bending towards the normal or away from the normal, it is all due to the change in speed. Anyhow, that's all about refraction. Coming back, that why does blue bends more than red? I hope you all understand that. If someone asks you why does blue bends more than red, simple answer, because blue has shorter wavelength and it interacts more than red with any medium, therefore it slows down further. Clear? Now, same prism I'm taking, this time I'm shining white light. So what do you mean by white light? It contains all V, I, B, G, Y, O, R. Okay, so if this is the bending of a violet light, that is the bending of a red light, because red bends lesser than violet. Similarly, if this is how the red bends away from the normal when it emerges out in air, blue bends even more than red. So if I keep a screen here, on the screen I'm going to see a red spot and a violet spot in this position. Sir, that's violet and that's red, but what about the remaining colors? They all lies between them. V, I, B, G, Y, O, R. So that's the order. So make it simple that the violet bends the most, that's why it's always at the bottom. Red bends the least, that's why it's always in the top. If you see any rainbow, let me go through, let me show you an image of a rainbow first. I'm sorry. That's a Rainbow Hospital. Rainbow. Right, you can see in this image here that red is on the top whereas violet is at the bottom. It's all due to the dispersion of light. Violet bends the most and red bends the least. Okay, so that's the understanding of dispersion of light. Next, let's do a problem. Light of wavelength 680 nanometers in air enters water, making an angle of 40.4 degrees with a normal. Determine the angle of refraction. So the question says here that a light is entering into water. Say this is a medium air whose refractive index is 1. I'm considering the top medium as 1, bottom medium as 2. So N1 is 1. Okay, entering into water whose refractive index is given, I'm considering that as N2 as 1.33. What is the angle made in air? It is 40.4 degrees. Now what is the angle of refraction? That is nothing but the angle in water. I'm considering that as theta 2. So with the help of Snell's law, which is sine theta 2 by sine theta 1 equals N1 by N2. That implies sine theta 2 equals sine theta 1 times N1 by N2. That implies theta 2 will be sine inverse of sine theta 1 times N1 by N2. So theta 1 is given, which is 40.4 degrees here. N1 is refractive index of air, 1. N2 is refractive index of water, 1.33. So let's plug in all the values. Sine inverse of sine of theta 1, which is 40.4 degrees. Please be careful here that the angles are in degrees. So your calculator has to be in degrees mode, but not radians. Times N1, which is 1, divided by N2, which is 1.33. If you simplify this, you must get 29.2 degrees. Okay, next. Second question says here the wavelength of light in water. So what is the wavelength of light in water? Same diagram again here. The light goes from air into water. It bends towards the normals. Angle of incidence is 40.4 degrees. Angle of refraction is found here, 29.2 degrees. N1 is 1, N2 is 1.33. So what is the wavelength of light in air? Lambda 1 is 686 nanometers. So question is to find out what is the wavelength in water, which is considered to be lambda 2. So again using Snell's law, that is lambda 2 over lambda 1 is equal to N1 by N2. From this I can write lambda 2 is equal to lambda 1 times N1 by N2. Lambda 1 is given, which is 686. Nano is 10 power of minus 9 meters multiplied by N1 divided by N2. So if you simplify this, you must get 517 nanometers. Clear? That's the wavelength in water. Now let's talk about the next concept, that is total internal reflection. Okay, for that I'm going to use a simulation here. Right, so you can see there's a source of light. I'm shining the light is traveling from air into water, and since it is traveling from a rarer medium, denser medium, it is bending towards the normal. Pretty much simple, we already know about that. So what I'm going to do is, like, I'll keep increasing the angle of incidence, that is from 44 to 45, then to 48 and 49 and so on. At no angle of incidence you find the reflected ray to be 100%. Okay, let me get an intensity instrument here. At no angle of incidence the reflected ray goes 100%. Clear? Let me increase the angle even further and further. So you can see at no angle of incidence the reflected ray becomes 100%. Right? So let's do something else now. I'm going to change the top medium to glass and lower medium to air, and we'll see whether the reflected ray becomes 100% at any angle. So you can see as I'm increasing the angle of incidence, the intensity percentage increases proportionally, right? You can see it just keeps on increasing as angle of incidence is increasing. That's great. At 42.3 degrees, or even maybe lesser than that, right? It's about around at 42 degrees. You can see all the ray is reflecting, right? My incident ray was 100%. All the reflected ray is also 100%. Now this phenomena, 100% means total, right? And the light is being reflected on the same side. On the same side is called internal. Since all the rays reflecting called total, phenomena is reflection. So total internal reflection. This phenomena is called total internal reflection. But what is total internal reflection? Total internal reflection is a phenomena by which all the incident ray reflects back to the same medium. You can see it's moving from glass to air. None of the ray is in air. Look at this. None of the ray is in air. All the ray is reflecting back. And this phenomena, what we call it as total internal reflection. So if you can check my PPT here, look at this image here. You can see a light, a laser light. Look at my cursor here. The laser light is shine, and as soon as there is a hole made here, the light, instead of going straight or traveling straight, it is traveling within the water. Look at this. The light is bending along the path of water, right? The light is bending along the path of water. So let us understand why, what is happening here. Obviously it is total internal reflection, but we'll conceptually understand that why is light ray is traveling within the water there. So if this is a bottle and the laser beam was shoot, the laser beam goes straight, but as soon as you make a hole here, let's say I make a hole here, let me change the ink color to red. Yeah, now the water is started falling down like this. Yeah, now you can see at this point here, the light is traveling from water into air. So this angle here, this angle of incidence theta here is beyond critical angle, which makes the light to continuously reflect within the water, due to which is basically total internal reflection. But wait, so what is critical angle? What is the critical angle there? So let's talk about here. You have seen that until 38.9 degrees or 39 degrees or 39.8 degrees or 40 degrees, at no angle the intensity was 100%, but only at certain angle the intensity has become 100%, right? This is called total internal reflection. But when, let me draw and show you here. Say I was shining the light from glass to water. You know that when the light ray is traveling from denser medium to rarer medium, it bends away from the normal. So that's how the ray bends, away from the normal. If I increase the angle of incidence, the angle of refraction will also increase proportionally. At one angle of incidence, you will find the ray goes parallel to the surface. Or we can also say the ray goes perpendicular to the normal. This angle is what we call as critical angle. I repeat, critical angle is the angle of incidence where the where the refracted ray goes perpendicular to the normal, or you can also say refracted ray goes parallel to the surface. And this angle of incidence here is what we call as critical angle. Clear? Now what if I increase the angle further beyond this? Or what I'm trying to say is, what if I increase the angle of incidence greater than critical angle? I'm calling that angle to be alpha, right? This alpha is greater than critical angle. In this angle, or at this angle, no ray will refract. All the ray will come out of the medium, right? All the ray will come out and travel in air. This phenomenon is what we call as total internal reflection. So first thing first, that for TIR to happen, I'm writing here, for TIR to happen, the angle of incidence must be greater than critical angle. Second thing, that the ray must travel from denser medium to rarer medium, right? And you have seen that when the ray was traveling from air to glass, you have not seen TIR to happen, right? You have not seen TIR to happen. At no angle you have seen all the ray reflect back, right? 100% reflection is not seen when the ray was traveling from rarer to denser. But when the ray is traveling from denser to rarer, that's when you see TIR to happen. So what is the second condition for TIR to happen? The ray must travel from denser medium to rarer medium. Okay, so this is about TIR and the two conditions for TIR to happen. Let's move to the next topic. Let's talk about diffraction. Okay, so what is a diffraction? Diffraction is basically a phenomena by which a wave spreads out when it's traveled through an obstacle, through a gap or around an obstacle. Okay, look at this image over here. You can see that these are the linear waves coming in, right? You can see those are linear waves coming in. But as soon as they're passing through this small gap over here, the linear wave turn into a circular wave like this, right? And this phenomena, this spreading out of a wave, right? The spreading of a wave is what we called as diffraction. Okay, so let us understand why diffraction happen. So if I have a small narrow gap, hypothetically, or let's say, what do we predict? If this is how the wave is traveling, we would predict that this small region of the wave will be passing through this narrow gap, and the remaining part of the wave should bounce back after hitting this boundary. Yes, that's what we assume. Forget about diffraction. You don't know anything about diffraction. Just think this portion of the wave will pass through this small narrow gap and should go straight like this. And if I have a screen here, I will be able to see a bright spot at the center, because that's the portion where we have light now, right? The coming light is of this width, the incoming light is of this width, but assumption that if light, the small portion of the light is able to pass through that narrow gap, I will be able to have a small spot on the wall. This is what we obviously think, isn't it? That, sir, I'll just shoot a light through a small gap, and that's through the small gap on the wall I should see a small spot. That's it, right? But that doesn't happen. Instead, you will find that consecutive bright spots, dark space, bright spot, dark space, bright spot, dark space, bright spot, dark space. But wait, forget about the bright spot, dark space, forget about the dark spots between them. They are insignificant. I'm not interested to talk about them. But why we have so many bright spots? I mean, according to my theoretical or very basic understanding in physics, that the ray should go straight and hit the wall there, and I should have only one spot there. Why we have so many bright spots in the wall? That means the wave is not just traveling straight at this point, the wave is also reaching to other points on the wall. That's the basic understanding. And that's what we call as diffraction, as simple as that. This phenomenon is what we call diffraction. But why does a wave travel in every part of the wall instead of only one part on the wall? It was very difficult to explain. Many scientists failed to even bring a theoretical model to explain this properly. But finally, Fresnel and Huygens, I'm writing down the name here, Fresnel, Fresnel and Huygens, they didn't work at the same time. They worked at different time period. But finally, they both worked under the same concept. That's why this principle about why diffraction happen is said to be Fresnel and Huygens principle. Okay, so what Fresnel and Huygens tried to explain through theoretical model, they assume that the wave that we're drawing, those are basically your wave fronts. We have already learned what is wave fronts. They are the imaginary line drawn through the crests, right? So what they have thought that what we see is the primary waves, right? What we see is the primary waves, but there could be secondary waves within the primary waves. Okay, they assumed that there could be secondary waves of spherical shapes like this. And they're not circle, okay, that they're like spherical, three-dimensional ball-shaped secondary waves. They assumed that for diffraction to happen, first of all, there must be a secondary waves of spherical shape within the primary wave that we already know. Okay, they named these spherical waves as secondary waves. What they also said that these secondary waves, the size of these secondary waves depends on the size of the primary waves. Basically, a wave with larger wavelength will have a larger secondary waves, and the wave with shorter wavelengths will have a smaller secondary waves. Okay, so what they're trying to actually explain, what they're saying is, like, say if you have a wave traveling, why there seem to be a linear wave, why there seem to be linear wave, according to them, because all those secondary waves are too close together that they overlap with each other. Okay, let me just quickly draw all the secondary waves. Okay, you can see all the secondary waves are overlapping with each other and finally gives a flattened shape, a flat shape over here, starting from here until there is a flat shape because waves overlapping, right? The waves overlap, and you can see that overlapping is giving that flat shape, right? But at the corners, you can see the corners, this and this corner here, your waves are curved because there are no more secondary waves to overlap with the corner wave secondary waves. So that's why they clearly explain that the edges are curved. If you see any water flowing on over what do you take? You people can do the same thing. Take a glass of water, pour it on the floor. You'll find the middle portion may be traveling straight. The middle portion might be traveling straight, but the corners are curved. Why they're curved is because, according to them, this is a theoretical model. But they succeeded. They beautifully explain about the diffraction. So, okay. Anyhow, so what they try to explain is that all the secondary wave fronts are too close, that they overlap with each other. That is why they give a flat shape. Okay, I'm sorry, the camera was overheating, so it stopped. I'm resuming from here. So what I was saying, that the secondary wavelets, the secondary wave fronts, they overlap over here. You can see this overlaps very closely with the second one. That the second one closely overlap with the third one, and so on. They overlap too close together that they give a resultant to be flat here. But since the end wave fronts, the secondary wave fronts, do not have any other neighbors to cancel out, that's why the corners are always curved. Beautifully explained by them that why waves are flat in the center and why they're curved at the edges. Through them only, through this concept only, what they have explained is, when there's a small gate, I mean basically slit, there's a small gate, a narrow gate, if you are allowing a small portion of the wave, look at this is how the wave fronts are there, right? Maybe through the small gate, not all the secondary wave fronts are passing, maybe only say secondary wave fronts are able to pass through. With that small gap, only 3 secondary wave fronts are able to pass through. Due to which, what will happen? You will have a curved at the edges, obviously, and you will have a small flat in the center, right? So what is the shape of the overall wave front? That's how it will be, right? So that's how the wave front is. You can see the incoming wave front is linear, but the outgoing wave front from the slit is curved. It is, now when you know the wave front, how do you draw the ray? Rays are always drawn perpendicular to the wave front, yes? Rays are always drawn perpendicular to the wave front. So let's go ahead and draw the rays perpendicular to the wave front at each point here. Look at this. I'm drawing rays perpendicular to the wave fronts. You can see the rays are reaching every point on the wall. If I have a screen here, the ray is reaching at this point, the ray is reaching at this point, the ray is reaching that point, the rays are reaching this point. So this is why a ray, when passes through small slit or small narrow gap, it is able to spread out and able to reach every part of the wall. And this phenomenon is what we call as diffraction. So they said, what if the gap is too narrow? Let's make the gap to be very negligible width, due to which maybe only one secondary wave is able to pass through, due to which my wave front will be completely curved, no flat, complete curved, and this diffraction is said to be pure diffraction. So from this concept we understand that if your narrow gap here, which we call it a slit, I'm going to use the word slit from now onwards, if slit width is smaller, gives you purer diffraction, right? Or simply, if slit width is smaller, diffraction is higher. What if slit width is larger, say this much? Because a larger gate, more number of secondary wave fronts will be able to pass through, due to which the edges will be curved like this, but the center will be flattened up like this, and how the resultant wave front will be. Look at this. That's not a pure diffraction, right? So larger the slit width, larger, sorry for the mistakes here, spelling mistakes, is larger the slit width, smaller the diffraction. Yes. So this is how Huygens and Fresnel were able to explain why diffraction happened through the secondary wavelets or wave fronts. Okay, that's all about diffraction. So what are the conditions for larger diffraction? The first condition is that larger the slit width, smaller diffraction, smaller slit width gives you larger diffraction. The second factor that affects the diffraction is the wavelength. Sir, why? Let's take, I'm sending two waves of different wavelengths. This is wave number 1 of wavelength lambda 1, and I'm sending second wave of smaller wavelength. You can see from the diagram itself, the second wave has lesser gap between two consecutive wave fronts, so lambda 2 is lesser than lambda 1. And I have already discussed in the top that Huygens and Fresnel principle also states that larger the wavelength, larger the secondary wave fronts, smaller the wavelength, smaller the secondary wave fronts. So that is what this explains, that which gives a greater diffraction. So larger wavelength will have a larger secondary wave fronts like this, whereas smaller wavelengths will have a smaller secondary wave fronts like this, right? So in this case, look at this, because the larger secondary wave fronts, only one may be able to pass through this gap. But because of the smaller secondary wave fronts in the second case, maybe 3 secondary wave fronts will be able to pass through that same given gap. It's the same width here, okay? So what is the shape of the wave front passing through? That's how it is, pure curved, whereas here edges are curved, center is flat, curved, flat, curved, curved, flat, curved. So which is a pure diffraction? This is pure diffraction. This is less diffraction. So we understand from this observation that larger the wavelength, larger the diffraction, smaller the wavelength, smaller the diffraction. Okay, so what are the conditions for larger diffraction? Slit width needs to be smaller, wavelength needs to be larger, right? Opposite will give you lesser diffraction. So that's all about diffraction. Let's move to next concept, that is double source interference. Okay, we'll see this in our next video.